This is Screencast for section 4.3, example 8. We're going to use f prime and f double prime to graph f. Now we've already done this in a previous example, but this is officially where the book introduces it and practice makes perfect, so we're going to do it again. Alright, so let f prime, so they give you the first derivative already, equal 4x cubed minus 12x squared. Identify where the extrema of f occur. Well, we've already got f, we've just got to find its zeros and test those on a number line, so the first derivative test. So I found that the first derivative equals 0 at x equals 0 and 3. So on this first derivative, I'm going to test each of these intervals, and I actually get that 0, although a critical value, is not an extrema. The only extrema that f has is a local min at x equals 3 because the derivative changes from negative to positive, first derivative. Therefore, f would change from decreasing to increasing. Part B, find the intervals on which f is increasing and the intervals on which f is decreasing. Well, luckily for us, we've already done the work for that, so we don't need to do it again. We can just use this number line test. F is increasing from 3 to infinity. Now, you cannot say that f is decreasing from negative infinity to 3 because for the instant at 0, f is kind of constant. It's just not decreasing. So we have to say from negative infinity to 0. And then from 0 to 3. And because f is increasing, I got that from where f prime was positive, the first derivative was positive, and f is decreasing where f prime is negative, so those two intervals there. Part C, find where the graph of f is concave up and where it is concave down. Concavity is given to us by testing the second derivative. So I have to find the second derivative, find its critical values, and test its intervals. So the critical values of f double prime are 0 and 2. So I've got, let's see, I'm going to test these intervals here. I got a positive, a negative, and a positive. So I have inflection points at 0 and 2 because the concavity changes, but that's not what it's asking me. It's asking me where f is concave up, so where the second derivative is positive, and that's going to be from negative infinity to 0, and then 2 to infinity. And then f is going to be concave down between 0 and 2, where the second derivative is negative. Now, sketching this possible graph of f is going to be a little tricky because before, when we sketched it, we had actually a graph in front of us to see. So now we're going to have to kind of go off of this analysis that we've done in parts A through C. So I'm going to use the same strategy I did before. I'm going to do like a partial sketch. And I've got some important values that I see here, 0, 2, and 3. So I mark those on the x-axis. Now my increasing, decreasing, I get from f prime. So we're decreasing from negative infinity to 0. But then I've got this flat spot at 0 that I'm going to kind of mark there. And then I decrease again from 0 to 3. And then from 3 to infinity, increase. So there's some sort of minimum there at 3, like we said before. Now, the concavity pass, I can see from negative infinity to 0, I'm concave up. And then from between 0 and 2, concave down. But then there's an inflection point at 2, which was not marked there. And then from 2 to infinity, concave up again. So now I can make my final sketch. From negative infinity to 0, nothing really exciting happens. Concave up, decreasing. So I'm going to put a point on the y-axis there to go to. Concave up, decreasing. Then we have a horizontal tangent, so I kind of want to make that a little bit obvious, I guess. And then we're from, let's see, 0 to 2, concave down, decreasing. So maybe I'll put that point right there. Then from between 2 and 3, concave up, still decreasing. But then from 3 to infinity, concave up, increasing. Now your graph might not look as skewed. Maybe your points were a little bit closer together. Maybe yours were more dramatic vertically. I don't know. But you know, this is the general shape that your sketch would take. And of course, I'm going to label this as f. This is not f prime. This is not f double prime. This is a sketch of f. The now try problem for number 39 is asking us for pretty much the same stuff. We've already got y prime. It's factored. We're going to do a little bit of an analysis, and then we're going to sketch a possible graph. So here we go. Y prime, again, already factored. So if I set it equal to 0, I do see that I get x equals 1 and 2 as critical values. I can draw a number line, label that with y prime, and test the intervals. So I see that there is actually no maximums on the graph of f, because nowhere does the first derivative change from positive to negative, making the original function change from increasing to decreasing. This change here at 2 is a local min. The original function would change from decreasing to increasing, creating that local minimum. So y has a local min at x equals 2. Now a point of inflection has to be found by the second derivative, so that's going to involve a little bit more work. Now you may be thinking to yourself, okay, do I multiply all this out and then take the second derivative? Well, you could, but then you'd have to factor that. I mean, that is definitely an option. I'm going to choose to use the product rule. I'm going to make x minus 1 squared u and x minus 2 v when I take the derivative of y prime. So y double prime then would equal, let's see, I'll take the derivative of this x minus 1 squared. So that's 2 x minus 1 now to the first, and then leave x minus 2 alone, plus, now x minus 1 squared gets to stay there, but then the derivative of x minus 2 is just 1, so that's nice. Now both this guy and this guy have an x minus 1, so I'm going to factor out that x minus 1, which then leaves me with 2x minus 2 plus x minus 1 and a 1 on the inside. So I'll simplify that inside of the parentheses, and I get that the critical values here are 1 and 5/3, so I'm going to test those on a number line. So my inflection points are both at 1 and 5/3 because the concavity changes in y at both those spots. Now with our two number line tests here, first derivative test and kind of second derivative test, we can sketch a possible graph for f pretty easily, even though we aren't looking at the graph as we saw in the last example. My important values here are 1, 2, and then of course 5/3, which is going to be kind of in there. So my increasing, decreasing paths from negative infinity to 1, I'm decreasing. I've got a flat spot here at 1, and then between 1 and 2, still decreasing. So I'm gonna decrease down here to get out of the way of the 5/3. Then from 2 to infinity, I'm increasing forever. Now the concave up, concave down pass, concavity pass. From negative infinity to 1, I'm concave up. So this whole time, concave up. Then 1 to 5/3, concave down, so there's this inflection point somewhere here around 5/3, and then concave up for the rest of the time. It's looking a little jumbled there, so let's clean this up on a nice new graph. Here's 1, here's 2, here's 5/3. Alright, so negative infinity to 1, very boring, decreasing, concave up. I got a flat spot here at 1. And then from 1 to 5/3, concave down, decreasing. Inflection point at 5/3, and then, let's see, between 5/3 and 2, concave up, decreasing. And then from 2 to infinity, concave up, increasing. So even though this graph, my sketch, dips below the x-axis and my final one did not, they still both accurately represent what my first and second derivative are telling me about the original function. We don't really get into specific y values until chapters 5 and 6 when we're talking about antiderivatives.